this is example 2.2 from the course text, and it illustrates the a graphical interpretation of the convolution sum that we have talked earlier. Uh, so if you recall the output y of n of a discrete time LTS system, uh, to which then input x of n is applied, okay, the output, since the system is linear, will consist of the superposition of the weighted impulse responses of the system. Okay, so h of n is the impulse response of the system, and xk's are the samples of the input, which forms the weights of the impulse response h of n. Okay, now you see, to evaluate this convolution sum, you can do this graphically as well. So what it means is that if you treat your input sequence as a function of k, since the summation is over k, and you have to sum all the impulse responses, okay, since x of k can be also be decomposed in terms of the impulse sequences, therefore to delta of n you have h of n as the impulse response, and for each shifted impulse you have a shifted impulse sequence, impulse response, okay, the same number of delays, time invariant as well. Then due to the superposition, you sum all these individual responses, okay, and then weight them by the corresponding x of k's, which are the scalars or the weightings of the impulse responses. Now, what this expression means graphically is that if you treat the sequence as a function of k, then this function is the time reversal of the impulse response. So that means this is h of minus k, okay, which is simply shifted, which is shifted for n, for a fixed n, okay. So that means if you have to evaluate it for a particular n, then you have to shift the sequence. This is the time reversal of the impulse response, and you have to shift it for that particular discrete time index n, okay. Now n can be greater than 0 or it can be less than 0, okay. So if n is greater than 0, if n is a positive quantity, then h of minus k is supposed to be shifting towards right, okay. If n is less than 0, so this is for n less, this case is for n greater than 0, it's going to shift towards right. If n is less than 0, if n is less than 0, then this impulse sequence is going to shift towards left, okay. So for the corresponding shift, you have to multiply this with the sequence x of k and then sum all the samples. Okay, as an example, you see, let's consider the same example we talked earlier in example 2.1. So my sequence h of n, which is the impulse response of a LTS system, and the input is the same, okay. The samples, the number of samples, and even the sample itself, they're the same, okay. So we have the same sequences, h of n and x of n. So we are not going to consider the linearity principle behind the convolution, which we talked of, because x of n can be decomposed into delta n functions, okay. And so what we did was, since x of n, this is 0.5 delta of n, then we make this as 0.5 h of n. Similarly, this was a delayed delta function, this was twice delta n minus 1, so we had this twice h of n minus 1, and then we add these two sequences to produce y of n, okay. Well, this is the interpretation behind linearity, behind the principles of linearity and time invariance, okay. But we are going to consider another approach which we can use to solve the convolution sum. That's the graphical approach. So we're starting with the same sequence x of k. Now we are considering the sequence as a function of k. K is my discrete time index, okay. So there are two samples. At n equal to 0, x of k is 0.5, x of 0 is 0.5, and then k equal to 1, x of 1 is 2, right? Then similarly, okay, now instead of considering h of n as it is, which is 1 for all the three samples from 0, 1, and 2, we consider h of minus k, okay. We consider h of minus k, and if you can figure this out correctly, this is the flipped version of h of n, okay. So what you have is, you will have a sequence like this. At n equal to 0, then you have it at n equal to minus 1, and then there will be the last sample at n equal to minus 2, right? So this is the flipped version of your impulse sequence h of n, so minus 1, minus 2, that's it. Okay, this is my h of minus k. Now I'm going to shift this towards left, towards right. Okay, so you see over here, this is h of minus k. This is 0, -1, -2. Now, uh, to evaluate, so for example, this evaluation is done for this shifting uh, for h minus k is done for the discrete time indices n which is less than 0 or negative, which means your sequence is going to shift towards left. Okay, the sequence is going to shift towards left. So for n less than 0, my shifted impulse sequence, my reflected or flipped impulse sequence is going to shift towards left. Okay, so what I'm trying to do is, first of all I'm trying to treat my sequence as a function of k, since the summation is over k. Okay, so I don't have n over here, I have k. Okay, then instead of considering h of n, I'm considering h minus k. I'm starting from h minus k. Okay, so let's start from this point. And so I have h minus k, and then I'm going to shift this for a particular n. Okay, and n is again an integer, which can be positive, it could be negative. So if it is negative, then the shift comes towards left. Okay, like this. So these are the shift towards left for n less than 0. Similarly, for these four figures, you see n is positive, n is 1 over here, 2, 3, so it's positive. So these shifts happen towards right. So this is for n greater than 0, and you see the sequence starts shifting towards right. It starts shifting towards right. So instead of considering xk and hk, I'm considering xk and h minus k, and then I'm shifting this on either side. So I'm considering all the positive values of n and all the negative values of n. Now consider what happens next. Okay, I have the samples. I have the shifted versions of the flipped impulse sequence h minus k, shifted flipped version of the impulse sequence. Okay, this is my flipped version of, this is the flipped version of my impulse sequence, which is shifted at a particular n. Okay, because I have to evaluate the sample of for evaluation of a particular sample of the output at n, I have to shift it by the same amount n. Okay, now uh, the other thing is shifting is there. You can see in this indices n minus k, and we are treating this as a function of k, both h and x sequences. Then comes the multiplication. Okay, there's a multiplication of the sequence xk and hn minus k, and then you have to sum all the samples. Fine. So for example, over here, this is for n less than 0, and if you see, there is no overlapping. So there is no non-zero sample which overlaps for n less than 0. So even for n is equal to -1, you are going to start from -1 over here. Okay, so you don't have any. You're going to start from here. Okay, then you have the three samples. So there is no overlapping, which means that y of n will be equal to 0 for n less than 0. Okay. Do you understand that? Do you see? The idea is that for n less than 0, you have to shift the whole impulse sequence. This was the original impulse sequence, okay, and you have to shift this towards left. When you shift towards left, when you have to shift this towards not exactly, you have to first flip this, okay. So let's have the flip version, and this corresponds to a situation like this over here. And once you flip this one sequence towards left like this, so you again have three samples, but then they're not going to start at 0, they're going to start from -1, -2, and -3. Okay, now you consider the sequence h of -1 minus k, and this is for n equal to -1, this is for n equal to -1, n equal to -1. Now if you think that this is k and this is x of k, then the expression becomes, if you put this in the convolution sum, my expression becomes y of n, which is at n equal to -1. So this is -1, okay, which is equal to x of k, h of -1 minus k. Okay, So there's a multiplication of these two sequences now. And then you have to sum all the samples. But then what are you multiplying? I mean, look at this sequence. You have to multiply this sequence with this sequence. This sequence has to be multiplied by this sequence. There's no non-zero sample which is overlapping, right? There's no non-zero sample which is overlapping between these two sequences, right? So therefore, your y minus 1n is identically equal to 0, okay? Which means y of n is 0 for n less than 0, for n less than 0. So graphically, this is the interpretation. The graphical interpretation is that you see this fact over here in this in part C as well, that y of n, you don't have any sample of the output y of n for n less than 0. It's all 0, okay? Because there is no non-overlapping sample, because in the shifted version of h minus k, when you shift it towards left, there is no overlapping, therefore there is no multiplication. The multiplication yields 0, okay? So therefore your y of n is 0 for n less than 0. That's the first thing to note over here. Then if you proceed for n greater than 0, for n greater than 0, then for n greater than 0, h minus k, the flipped impulse sequence has to shift towards right, okay? So now if you see in these figures, this is one shift towards right of h minus k. Remember that this is h minus k. Now we are not considering h of k or h of n. We are considering the flipped version of impulse sequence, okay? So this is one sample towards right, then another sample toward right makes h2 minus k, another sample that makes h3 minus k. Now note that for this, if I multiply this with my x of k, right, which is where, which is here, this is my x of k, okay? I see that there are two samples which are overlapping over here. So one overlap comes over here, the other overlap comes over here, okay? So what does this expression mean? This expression means that for y equal to 1, for y1, my expression becomes this summation is over k, okay? So I have to sum all the samples over k. This becomes x of k, and then h of 1 minus k. So what happens on sample to sample multiplication basis? What happens is that if I consider this sequence with this sequence, there are two non-overlapping samples. So the multiplication yields, this is 0.5, and then this multiplication of 2 with 1 is again 2. So basically the result is equal to 2 plus 0.5, okay? So y of 1 is 2.5, y of 1 becomes 2.5. Similarly, if I have to evaluate y0, then that is simply again the summation. So you have to sum all the samples of what? Of xk multiplied by h minus k. First you have to see how many samples are there which are overlapping. Just multiply them sample to sample basis and add them up over k. Okay, so that's the interpretation. So for example, over here in this sequence and in this sequence, if you consider these two sequences, there is only one overlapping sample, that is 0.5. So this overlaps with this sample. Nothing else is overlapping. So that means your y of 0, I can write y of 0, if you can see this correctly, y of 0 will be 0.5. Okay, y of 0 is 0.5. Similarly, my y of 1, just look at this graphical representation of the convolution sum, and you can evaluate the output samples at n equal to 0, n equal to 1, n equal to 2, and so on and so forth. So what happens at n equal to 2? We have two overlapping samples. So let's just see over here. This is y equal to 1. Okay, this is y equal to 1. So this multiplication is basically, this is 2.5. You can see this quite clearly. Then once you are you make another shift toward right, you increase n by another sample, so n becomes 2 over here. Then my y2 becomes equal to how much? You see, again I have two samples, okay, which are overlapping. So again the result is the same, 2.5. And then finally when I have this shifted by another sample, so n becomes 3, n is equal to 3, or in this case, n is 3, okay, so n is 2. So all we are doing is we are varying the sequence for a fixed n. N is the variable, okay, n is the shift variable, I would say. N is fixed in all these graphs, okay. N is fixed in all these graphs, but n is varying, okay. So for these, as you go downwards, this is for positive integer values of n. This was for n less than 0, okay, which produced no overlapping. So for fixed n, we are shifting the sequence, okay, in each graph. Now this has just one overlapping. There's only one overlapping sample at n equal to 1. There's no overlapping at n equal to 0 or n equal to 2 either, okay, because the 2x of k is 0. So 1 multiplied by 2 is 2, okay. So y of 3 is 2. Do we have more overlaps? So let's see if we shift this by another sample. So if at n equal to 4, what's going to happen is this, that the sample at n equal to 1 will be there at n equal to 2, and n equal to 2 sample will be at n equal to 3, and again there will be no overlapping, okay. This sample is going to vanish, okay, which means there's no overlapping. So that means y of n is again 0 for n greater than 3, okay. We had this overlap up until n equal to 3. So from 0, this is n equal to 0. From 0 to 3, we have non-zero overlaps. Therefore, the multiplication is possible and summation is possible. Therefore, we have the convolution sum that exists, and it exists for n equal to 0 to 3. Okay, so again, what it says is that let us consider again the convolution problem that we encountered in example 2.1. So if you recall, we considered the same impulse sequence and the input sequence. The sequence x of k is shown in figure 2.4a, while the sequence hn minus k for n fixed and viewed as a function of k is shown in figure 2.4b for several different values of n. So yeah, we started with the x of k, and we treated both the sequence xk and hk as a functions of k's, okay, and then we start shifting them for the given n, okay. For n equal to 0, this is just a flip version of the impulse sequence, and then for n equal to 1, we started shifting it towards right for because n is positive. For n greater than 3, there is no overlap, so we just stop there. So this is the graphical way of looking at this shifted impulse sequence, okay. Shifted flipped impulse sequence, I would say. Now in sketching these sequences, we have used the fact that hn minus k viewed as a function of k with n fixed is a time reverse and a shifted version of impulse response h of k. Now in particular, as k increases, the argument decreases. That means this explains the need to perform the time reversal of hk, okay, because this argument is varying with k, right? This argument varying with k. So knowing this, then in order to sketch the signal hn minus k, we need to only determine its value for a particular value of k. For example, the argument will be equal to 0 and k equal to n, right? So that means you are evaluating, when k equal to n, you are evaluating y 0, right? Because this argument becomes 0, right? So for n equal to k, you are evaluating this is actually y. In general, this is y of k. Okay, this is not. In general, this becomes y equal to k because n is equal to k. Now, thus, if we sketch the signal h minus k, we can obtain the signal n minus k by simply shifting to the right by n if n is positive, or to the left if n is negative. The result for our example for the values of n less than 0 and for n greater than 3 are shown in figure 2.4b. So this is 2.4b, and you can see the shifts for particular n, and this figure is for n less than 0. So having sketched xk and hn minus k for any particular value of n, we multiply these two signals and sum over all values of k. For example, for n less than 0, we see from 2.4 that there's for all k, the non-zero values of xk and hn minus k, they do not overlap. Okay, so there is no overlap. So consequently, for y of n is 0 for n less than 0. So for n equal to 0, the product of the sequence xk and the sequence has only one non-zero sample with a value 0.5. You can see over here uh, there's only one non-zero sample 0.5, which multiplies with h0 minus k, and the result of y0 becomes zero point 0.5 over here. Similarly, for y1, there are two overlapping samples. This produces 2.5, and the same situation appears at n equal to 2. You have the output sample at n equal to 2 as 2.5. Fine. This is for h2 minus k, which means n equal to 2. Then for another shift towards right, H3, there is only one non-zero overlapping sample. This produces Y3 as 2. And then for n greater than 3, there is no overlap, so there is no convolution sum. Okay, so these are the this is the result. If you put y1, then n is 1. That means you have to shift the flipped version of the impulse sequence by one sample to the right. Okay, and then multiply the two sequences, add them up over k, and then you obtain the value of the output at n equal to 1. This is the output at n equal to 1. This is the output at n equal to 2. And then finally, you have the output at n equal to 3 as 2. Okay. You don't need to go any further because there is no overlap. So you can either expand this convolution sum as a summation, do it analytically, or you can do it graphically. So this is what the graphical approach illustrates. Basically, you have to flip the impulse sequence, and then you have to multiply the sample by sample basis. Those samples which are overlapping, with those samples which are not overlapping, don't bother about them. So finally, for n greater than 3, the product is 0 for all k, from which we conclude that y of n for y of n is 0 for n greater than 3, and the resulting output agrees with that obtained in 2.1. So you see that the output y of n that we have over here, y of 0 is 0.5, y1 2.5, y2 is 2.5, y3 equal to 2, is exactly what we had before when we sum the two sequences 0.5 h of n and 2h n minus 1. So this is 0.5 for y0, 2.5 for y1, 2.5 for y2, and then finally 2 for y3. Okay, so this agrees with the previous approach as well. So now the purpose was just to explain you that there is a graphical way of looking at the convolution sum, and for that graphical way you have to work with the flipped impulse sequence. So you can flip the impulse sequence, and then you can start shifting it towards left and right depending on which particular output sample of the output you have to evaluate for that particular n. If the samples are overlapping, just multiply those samples with the input sequence x of k and then sum them up. Okay, and do it for those values of n for which you have a non-zero output y of n, right? So that's the idea. Okay, so that's the idea. Okay, that's all.